Hello viewers, welcome to my channel Learn Electrical Engineering 121 Pod. Hello viewers, in the last session we have seen the mathematical approach of control systems. We have seen how to relate an output to input, and finally we have arrived at the mathematical expression called transfer function in terms of relating output and input in terms of Laplace domain. In today's session, we'll see the mathematical modeling for mechanical systems. Let's see what those are. In these mechanical systems, we do have two types. One is translational system, and the second one is rotational. Now, today we'll see the very first type, mechanical translational system. And in this system, we do have certain variables. Those variables are variables defining this mechanical translational system are x, that is nothing but displacement, and velocity, and then we have acceleration. Okay, now x is displacement, v is nothing but dx by dt, and acceleration is given by d square x by dt square. We have seen the variables for mechanical translational system. Those are nothing but x, v and a. Then we have characterizing elements. Those are mass represented by m. Then we have dashpot represented by a piston in a cylinder, a moving piston in a cylinder where you have the viscous fluid here. Now, the next one is spring. Okay, so these are the variables of that particular system, and these are the characterizing elements which define that particular system. In mechanical translational systems, the applied force is equal to sum of opposing forces. Okay, now for example, if applied force is say F, that is equal to opposing forces are due to, one is due to mass, then the other one is due to the damping force or the viscous friction, or due to dashpot, you call this as FB. Okay, and another characterizing element, that is spring, or you call this as friction due to elasticity, Fk. Okay, if applied force is F, say, then you have three opposing forces with respect to three characterizing elements. Those are mass, dashpot and spring. Now, for finding the mathematical approach or the model for this mechanical translational system, let's see what are the parameters involved. Now, x is nothing but displacement in meters, and v is velocity dx by dt in meters per second, and A is acceleration d square x by dt square in meters per second square. Now we have applied force F, say, that is in newtons, and due to the characterizing elements of that system, the very first opposing force is Fm, that is opposing force due to mass in newtons, and then we have Fb, that is the opposing force due to friction or viscous friction, you call it due to friction due to damping force in newtons. Then we have Fk, that is nothing but opposing force due to elasticity or due to spring. Here we have m, that is nothing but mass, k, that is stiffness of the spring, and b is viscous friction coefficient. Now we'll see the force balance equations, okay, for this mechanical translation system. Now the very first case, we consider an element where the other two factors, that is the spring and the dashpot, are being negligible. The other two characterizing elements are absent here. You have only mass present here. This is an ideal case where the other two factors are absent here. Now on this, we have an applied force, say F. Then you have a displacement x, say here. Okay. Now already we have a condition called applied force, say F is equal to opposing force. Here you have only opposing element, that is only the mass here. So definitely you have only the force due to this mass here, that is acting in opposition with the applied force. So F equal to Fm. Now this Fm is proportional to d square x by dt square, nothing but equal to m d square x by dt square according to Newton's second law. Now for the second case, where we have only dashpot, where the other two elements, that is characterizing elements mass and elasticity, is absent, where you have applied force F and the displacement x. Okay, then applied force is equal to opposing force, where you have only the element dashpot here. Obviously F is equal to applied force equal to opposing force, and Fb is equal to b into dx by dt. This is according to Newton's second law. Here in the same case, where we have an element only with this dashpot here, okay, where you have two displacements x1 and x2, say, that is being displaced at both the ends here, then applied force is equal to opposing force, that is as usual. But whereas the opposing force is equal to b into d by dt of difference of this displacement, or on the whole this is the difference of the velocities. Now in the third case, we have the third characterizing element, spring, here, where the mass and dashpot are absent here. Okay, this is an ideal case where the force F being applied, you have the displacement x here. Now applied force F is equal to opposing force Fk, and Fk is equal to Kx. Now in the same case, where we have displacement at both the ends, x1 and x2 are the displacements, say, then applied force is equal to opposing force Fk, and Fk is equal to K into difference of this displacement. Now once we come to know about all the parameters involved and the individual elements representation, Finally, once you have all the combination of these elements, what we do is we do first frame the free body diagrams of different elements at that particular nodes and represent the force and the displacement and draw the free body diagram, and then you apply the condition applied force equal to opposing force at each and every node. Usually those nodes are nothing but the mass elements. Okay, it's not really necessary this should happen in every case, but most of the cases wherever you have the mass element, it is considered as a node where you are supposed to draw the free body diagram, then apply the condition applied force is equal to opposing forces and solve all those differential equations, and then finally we can find the transfer function for that mechanical translational system. Okay, in today's session we have seen what mechanical translation systems are and what are the characterizing elements and what are the variables involved in that, and individually how do we draw the free body diagram and apply the condition applied force equal to opposing force. And in the next session we'll see an example of this mechanical translation system. Will solve a problem so that we can clearly come to know how to apply the free body diagram and how to write the mathematical frame in terms of differential equations, and then finally how to find the transfer function. If you do have any suggestions and queries, please mention in the comment box below.
Thank you for watching. If you find this video helpful, please like, share and subscribe. Stay tuned for more videos.